This presentation is about AVL trees. The key property of an AVL tree is that the heights of the two child subtrees of any node differ by no more than 1. This ensures that the AVL tree maintains a low height, facilitating faster operations. The AVL tree self-balances by rotations, which we will talk about later. I'm going to show you an example of a valid self-balanced AVL tree and a non-valid AVL tree. On the left, we have inserted 6, 4, 8, 7, and 9. The left and right subtree height difference of 4, 8, 7, and 9 are 0. For 6, we could see that the height of the left subtree is 1, and the height of the right subtree is 2. The difference between 1 and 2 is just 1, so it is a valid AVL tree. On the other side, we have inserted 5, 4, 8, 3, and 2. This tree isn't an AVL tree since just node 5 has a left subtree height of 3 and the right subtree height of 1. The difference is more than 1, so it's not a valid AVL tree. The balance factor is the height of left subtree minus the height of the right subtree. It helps determine when to perform rotations. If the result is -1, 0, or 1, then the node is balanced. Let's look at balance factors for this example. When we inserted 5, the balance factor of 5 is 0 since the height of both left and right subtrees are 0. When we inserted 4, the balance factor of 5 is 1 since height of left subtree 1 minus height of right subtree 0 is 1. We can see similar calculations for inserting 9 and 11. When we insert 10, the balance factor of 5 and 9 is -2, making these nodes unbalanced. The AVL tree must then perform rotations to make them balanced. AVL trees use rotations as a tool to restore balance. There are 4 types of rotations: right rotation, left rotation, right-left rotation, and left-right rotation. The type of rotation applied depends on whether the imbalance is in the left-left, right-right, left-right, or right-left position relative to the node in question. Let's talk about left rotations. Left rotations are made when the tree is out of balance and right-heavy, which means the right subtree's height is larger than the left. As we can see in this example, for node root 5, the left height is 0 and the right height is 2. It is right-heavy. We need a left rotation to balance the tree. Right rotations are made when the tree is out of balance and left-heavy. As we can see in this example, for node 3, the left subtree height is 2 and the right subtree height is 0. 2 minus 0 is 2, which isn't -1, 0, or 1, so it is imbalanced and left-heavy. We do a right rotation to balance it. A left-right rotation occurs when a node has a balance factor of 2, meaning it's left-leaning, but its left child has a balance factor of -1, indicating that the left child is right-heavy. In this example, we have inserted 5, 3, and 4. Looking at the balance factors, we can tell this is a left-leaning tree, but the child is right-heavy. First, we do a left rotation. After the left rotation, our tree looks like this. It is left-leaning, so we do a right rotation. Let's update the balance factors. After the right rotation, our tree looks like this, which is balanced. A right-left rotation occurs when a node has a balance factor of -2, meaning it's heavily right-leaning, but its right child has a balance factor of 1, indicating that the right child is left-heavy. Let's look at this example where we inserted 5, 7, and 6. Node 5 is right-heavy and its child, node 7, is left-heavy. Let's do a right rotation. Now, 5 is still right-heavy, but its child is no longer left-heavy but right-heavy, so we do a left rotation.
So we're going to first start by looking at the code for this with deletion and what happens when we delete a node and it needs to be rotated to the left to remain balanced. So right now we have our tree, we can see that it's balanced, but we're going to delete 7. And so we can see that now this tree is right-heavy. Or that 8, the node 8 is right heavy. And one thing I do want to point out about delete, which is also the same for insert, and we'll talk about insert in this way as well, but for delete, we're going to traverse down a path to get to that node and then delete it, and then we're going to balance by going the opposite way. So we're going to, in this case, start at 8, check that's balance, and then go up to 6 and check that balance. And this is because of the recursive nature of delete. So first we're going to start with calling balance on 8. So we see the balance factor is 0 minus 2, which is negative 2. So now we're going into that else if statement, and now we have to check the balance of 8's right node to just make sure that we only need to perform one left rotation. So the balance of 9, you can see it's negative 1. So now we're going to perform a left rotation on 8. And this is just to show how we get our balance. It's just simply the left node's height minus the right node's height. And yes, so now we're going to look at the code for left rotation. This is the code for left rotation, which we are performing on 8. Right, so it's the new parent is 8's right child, which is 9. Wait, this makes sense. 9 comes up. The new child of parent is 9's left child. This is null. For the rotation part, the new parent's left child is 8. Right? 8 becomes 9's left child. And 8's right child becomes new left child of parent. That is null. So this is what this looks like. 9 becomes the new parent of 8 and 10. Right? 10 is the right child of 9. We didn't change anything. It was and is still is. But 8 is now 9's left child, and 9 is the right child of 6. And as we discussed with balance, it's still going to perform balance on 6, but this tree is already balanced, so nothing is going to happen. One thing to look at is deletion and how it handles new children of parents, because this obviously changes the values around. So left rotate will return 9, which is the new parent, and then we can see in this delete method that it handles that, right? So 6's right child will be that new parent 9 and its subtree. And so this deletion method handles kind of implicitly assigning new parents and their children, or assigning children to their parent after a balance switches the nodes up. And so that is our code for left rotation. So now we're going to look at when we have a tree that we just inserted into and it needs to be rotated to the right. It needs to have a right rotation. So our tree currently is balanced, right? The difference is no more than 1 in the heights of the subtrees. But when we insert 2, we can see that it's left heavy and therefore we need a right rotation. And I'm going to look at the insertion method really quickly just to explain how the recursion and balancing happens. So we can see that when the node is inserted into its proper place, it's just simply returned in its proper place. But then the rest of the nodes down here are balanced in the opposite way that the tree was traversed. So it comes down and finds where 2 needs to be inserted, and then because of its recursion, it moves up and balances the tree. So we're going to start with balancing 3. and its balance factor is 1, and so we don't do anything. And now we're going to call balance 4, right? We're moving up this way. And its balance factor is 2. So now we move into this if statement. And the next thing to check to make sure that we only need a left rotation is that the balance factor of its left node. So the balance factor of its left node is 3, and this is 1. And so now we see that we have to right rotate 4. This is the code for the right rotation, and so we're performing right rotation on 4. So the node is 4. The new parent is 4's left child, which is 3. That makes sense, right? 3 becomes the new parent. And the new right child of parent is new parent's right child, which is 3's right child, which is null. And so for the rotation part, the new parent's 3's right child is 4. Right? 4 comes down. And then 4's left child is the new right child of parent, which equals null. And so I'm just going to draw the subtree of 5. And then it's going to return new parent. And its subtree. So it's returning 3. And just something I think was good to look at is that in insert, the new parent is assigned the appropriate child reference of its parent node in these, right? So as it's going, it's implicitly assigning child references. And also, even though we see that our tree is going to be balanced after this rotation, it still is going to check the balance of 5 and still checks the balance of 7, right? It goes up the tree until it hits that root of the tree. So now we're just going to quickly go through a left-right and right-left rotation. And we're starting out with, as you can see, a left-right rotation after an insertion. So we've just inserted 3. And you can see that this subtree looks like what we went over in the beginning. So for this, as before, once 3 is inserted, we traverse up this and call balance on those nodes. So we're going to start with calling balance on 2. The balance factor of 2 is just -1, so nothing happens, and we call balance on 4, which the balance factor of 4, its left subtree's height is 2, and its right subtree height is 0. The balance factor is 2. So now we get into this if statement because the balance factor is greater than 1. And we check the balance factor of 4's left node, which is 2. And we already said that that is -1. So now we perform a left-right rotation on 4. And you can see down the bottom, first we start 4's left child is going to be the new parent that is returned after a left rotation on 2. So first we're going to perform that left rotation on 2, which looks like, right, 3 becomes the new parent, and then 2 becomes 3's left child. And now we perform a right rotate on 4. Right, and for that, 3 comes up and 4 becomes the right child of 3. 3 becomes that new parent. And then of course it would balance 7, but nothing would happen because the tree is already balanced. And then we have our balanced tree after a left-right rotation. And finally, we're going to perform a right-left rotation after a deletion. So in this subtree, we're deleting 6. And then, like before, it moves up and it calls balance on 10. The balance factor of 10 is 1 minus 3, right? Its left subtree is 1, and it's finally, we're going to perform a right-left rotation when we've deleted a node. So here we're deleting 6. And so it's going to move up and call balance on 10. The balance factor of 10 is its left subtree's height, which is 1, minus its right subtree's height, which is 3. So that results in -2. So now we move into this if statement. And next we check the balance factor of its right node, which is 15. So the balance factor of 15 is 2 minus 1, which is 1. So now we're going to right-left rotate 10. And first, we can see down here, we're assigning 10's right child to the new parent that is returned after it performs a right rotation on 10's right child, which is 15. So what that looks like, that right rotation on 15, we move 14 up, 14 becomes the new parent, 15 becomes the right child of 14, and then 11 remains the left child of 14. And above here, we're going to perform the left rotation on 10. So for this, right, 14 becomes the new parent. And then before, we didn't have to deal with it because it was null, but we have the new left child of parent, which is 14's left child. And so that is going to become 10's new right child. So 14 is the new parent, its right child is still 15. 10 becomes the left child of 14, who still has a left child of 5, and then that 11, which was 14's left child, becomes 10's right child. And here is our balanced tree after a right-left rotation.
Hi, so today we are talking about runtime of the AVL trees. Log n is the height of the tree basically, and n is the number of nodes in the tree of the AVL trees. So with methods like insertion and deletion, it performs balancing, which is like log n, and it traverses up the tree. Now the height of the tree is log n, as I said before, and it's the O of log n time is on average. And insertion deletions is to insert node, need to insert at the end of a tree or the first of the tree, and such as rebalancing tasks as well. Now we'll talk about some pros and cons of the AVL trees. Some advantages about it is that it has all the balanced height, which is log of n, and it has faster search compatibility because it's almost completely balanced with its balanced factors as -1, 0, or +1. Some of the disadvantages about the AVL trees is like longer potential runtime for insert and remove functions because of rebalancing afterwards, rebalancing rotations, and it does have some complex methods as well for rotations. Now, some of the applications about AVL trees that can be great use cases as well could be, for example, a dictionary, would be good because you're probably not going to be inserting new words again and every day or removing them once everything is set up. The search part would be used the most for a dictionary, and AVL trees are, as said before, made to be able to search quickly, so they can be really efficient in this kind of an application. Now let's talk about some of the other comparison of AVL trees with other type of trees like 2 and 3 trees or red black trees. So as you can see in here, AVL trees there does have a strictly balancing criteria like -1 plus 1 and 0, like completely balanced, but the pro about them is that they have really simple implementation to do that. The thing about 2 and 3 trees is that I have a lot of complications in their maintaining the code, maintaining the complex insertion and deletion operations. When we talk about red black trees, they prioritize quicker restructuring mechanisms over strict height balance, which is a pretty great pro for them. But the bad thing about red black trees is that balance is really less optimal than AVL trees comparatively. Overall, all three trees have same runtime of OF log n. Thanks.